In this video we will study some particular cases of self-supervised learning. The first one is this contrastive predictive coding. So the contrastive predictive coding is very much used in places where you have some kind of sequence or something related to space. So there's some kind of organization of the data in time or space. So for instance, let's say that we have a speech signal like this one. We divide it into pieces, and then each one of the pieces goes through an encoder. So the encoder is shared for all pieces, so they will produce some latent embedding, and then there is an autoregressive model on top of this. This is this recurrent networks that we also studied. So these recurrent networks will produce something that is called the latent context. So the latent context is depending on the current piece of signal through this encoder, but also on the previous pieces coming from these other recurrent connections. So this part is this part of coding, but then the coding has to be useful to do predictions of the next embeddings. So this is this part of predictive coding. So that is why it is called predictive coding. And the goal of these networks is to represent high-dimensional data. This can be done with sequences, as I showed here, but it can also be done with images, and we will see an example later. So the contrastive predictive coding, it maximizes the information between the input pieces in the future and the current context. That is our goal. And here we have this. So this is the definition of information between these two. So we will take this function here, f, and we will model that function in this way. So what we have is the embedding and the context, and the multiplication of the two will be a matrix that we also have to learn. So we want to maximize this information when this ratio is modeled in this particular way. And we will look for this function by minimizing the info in C. So you will take an anchor n-1 negative examples and try to minimize, to maximize this information. And the autoregressive part that we saw here is implemented by any one of the autoregressive, autorecurrent neurons, or layers that we already learned. These RNN, LSTM, GRU, etc. And this can be done also with images. So with images, you can have the sequence is somehow given by these patches, and then the patches have to be embedded into some space by an encoder, and then the encoder, the encoded and embedded vectors will be given to an autoregressive network. This autoregressive network will consider the previous embeddings, and they have to be useful to predict the future embeddings of the future patches. So you see the sequence, in terms of sequence, somehow is in images. It is not simulated, but interpreted as the spatial location of each one of the patches. Here we have another example of self-supervised learning. It is also the goal is to have useful embeddings of the patches. So here let's say that we have an image and we perform some data augmentation. So we do two data augmentation functions. So we have an input data and then we produce two augmentations. These two augmentations, they go through an encoder and they produce two embeddings of these two patches. And then these two patches are projected. So we have the projection of this patch through some network and some projection by the same network. And what we want is to maximize the similarity between these two embeddings. And this is done by the influence. So we saw this function in the chapter of losses, but here it is just a reminder. So we have n input images. For each one of the input images we produce an augmentation, so that is why we have 2n examples. And then in the 2n examples we try to measure, to maximize the similarity between these two embeddings and divide by the similarity of these two compared to any other example in the batch. So this is the similarity between 2k and 2k minus 1. So there, these 2k and 2k minus 1 are two different versions of the same image that have been augmented. And then we compute the distance between 2k minus 1 and k, and 2k, 2k, 2k minus 1, and we sum over all samples. So this SimCLR tries to minimize this. Okay, there is another, there are some problems, technical problems associated to SimCLR, especially with the size of the batches and so on. So this MoCo, that is a momentum contrast, aims to solve those problems. So on one side we will have this influence and the same kind of laws that we had before, but now the query will be different. So the query will be the procedure will be different. So the procedure, we have a query image. The query image goes through an encoder that produces some vector, and this vector will be compared to vectors coming from a kind of memory bank. This memory bank is has some. You have an image, you do data augmentation, and then that is the key, and then the key will have all the. So this memory bank will be updated over time, and then this key will be compared to the query. So the momentum encoder is has the same this key encoder here through the momentum. It has the same architecture as this one, but the weights are updated differently. So the encoder is updated through the standard backpropagation, but this encoder here for the keys, they are updated following momentum. So they start with the same weights, but then the weights of the momentum encoder are updated in this way. So all the other examples in the batch, they are considered to be negative examples. So the positive example is the augmented one. All the others, they are negative examples. And these negative examples, they go through the momentum encoder that produce different keys. And then these keys with this one coming from the query and an encoder here, they have to be useful to minimize this contrastive loss. That is somehow trying to do this thing that two vectors, one coming from the query, so the key vector coming from the query, the key vector coming from the data augmentation, they are similar, and all the others, they are dissimilar. If you are interested in this kind of techniques, you are encouraged to follow these links. They explain them very well, and this would be all for this extra information about self-supervised learning.